Today is a great day for us because Frontgrade Geisler announced the Grain. It's their next product. Grain is basically a combination of the Knoll 5 processor side by side with our hardware accelerator, Akida, which I will talk about today. It's a neuromorphic processor. That's why. That's why it is working with the principles of the human brain, and that makes it very flexible and at the same time very fast and also very power efficient. Just a few words to the company BrainChip. BrainChip was founded in 2004 in Australia, and the first many years were spent with research into making a neuromorphic chip or IP for the chip, and only in the last 3 years, basically, the Akida 1000 test chip was published, and with that, it is possible to sell the IP, and that's what we're working on at the moment. What I'll be talking about today is the points I want to show you a little bit about the philosophy behind Akida Generation 1. And then I'll show you some use cases, how Akida 1 was used in space use cases. Then I'll give you a bit of an outlook into Akida 2. That's the new version coming up now, and the background of the TENS state space model, which can run on the Akida 2.2 hardware. And then I will show you a few extended use cases which are only possible with Akida 2.0. Good. So basically, what is Akida? Akida is a neuromorphic in the sense of event-based AI hardware accelerator. It was made for the use at the edge, so very low power. And it is best suited for battery-powered applications or anything which is energy constrained, like space. When we say neuromorphic, that's what I said earlier. It works like the principles of the brain. It's not like the actual build-up, like with neurons and synapses and everything. That's not how we do it. We just, emulate basically how the brain works. Meaning, whenever nothing happens, like as long as there's not happening any event, the chip will not do anything. And only if events happen, then in the area of the event, the chip will do its work very efficiently. And so sparsity comes in really handy here, and makes the chip perform at a very low power level, but very fast, because only the calculations need to be done around the events themselves. The silicon is completely digital. That's why you can scale it with every process node, basically. As well as you can also scale it in the number of processing nodes that need to be integrated into the silicon. We sell IP, so it's not really the chip we sell, but it is it's the building blocks basically for like an ARM core. It's like the building blocks for putting the hardware accelerator onto silicon. How is Akida built up? What you can see here is an 8-node configuration, and we call it one of these is a neural node basically, and 8 of them together is what's going, for example, into the Grain processor from Frontgrade Geisler. Each one, if we just have a look at one of these neural nodes here you have like a microscopic image of it. You see there are the 4 NPUs, the neural processing units, in the corners. And in the middle, we have this greenish area, and that's what gives us the SRAM, which can be accessed by all 4 nodes. And that way we have a localized kind of memory, so there's no von Neumann bottleneck here. Right, it works in a synchronous way, not like Loihi, for example, or Spinnaker, which are asynchronous. We are synchronous. And all the communication going on the mesh here is basically it's basically happening like you push everything with the DMA. You push everything that needs to be processed on the mesh into the mesh, and then the mesh basically does its thing. Right. When we talk about TOPS, we are here in the order of magnitude of 1 TOP, and it is a little bit hard to actually talk about TOPS here, because when nothing really happens, there's basically running at zero TOPS, and if everything's running, then it's way more. If lots of events happening, then it is way more. But but that's the order of magnitude we're talking about here. Good. Right. So. How do you program Akida? Well, you can use basically TensorFlow, Keras. You can download models from our model zoo. They're pre-trained, and then you can send them to the MetaTF or the Akida model development environment. And then you can deploy it onto Akida. We do have a couple of partners, like Neurobus or EdgeX, who can help with anything that needs to that needs to be set up on the model side. So they can help. Good. So those are the use cases we No, I have to say it this way. Why would you need to put AI into space? Well, we heard that before. There are a couple of use cases here which need more autonomy on the side of the spacecraft. And this could be anything that goes into situational awareness here, or could be anything like space debris that might hit the space vehicle. Or it could be autonomous landing. Yeah, any of that basically. So we did have, or we are running right now. We are running a project with the European Space Agency in a consortium with Airbus, Neurobus, Geissler, and BrainChip. And we were looking at a couple of use cases because these projects are based on event cameras. And these event cameras basically only just show something that changes from one perspective to the next one. What you can see here is the lunar surface, and you're zooming in on it. And what you would actually see on this picture down here is just the rim of these craters here. And those are very high, they have a very high dynamic range. So with that one, you can actually see in the dark. And at the others it is very sparse, and you only see these events here, which is a perfect combination. These event-based cameras are a perfect combination with an event-based processing unit like it is Akida. So these are the 3 use cases we are covering together with Airbus, for the European Space Agency with Airbus. First one is the landing on the moon. Next one here is the rendezvous of 2 space vehicles. Also, both are set up with these event cameras. And the third one is the ship detection. It's a little bit of an extended version than what you have in the OBP ML benchmark, because I think it also gives you the length of the ships and the direction they're headed. Good. So that is possible with Akida as it is right now, Akida 1, which is integrated in Grain. Now, we didn't stop there. We continued our research, and that brought us to Akida 2.0, so second generation. And what we have, it is completed. The IP design is completed, and we can run it on an FPGA, as we have it right here. It's a Xilinx FPGA. So we can showcase it. We can prove it. It can be demonstrated together with a event camera, with a Prophecy event camera. Also runs these state space models here called TENS. What does that do? TENS is basically, it adds one more dimension here. We usually have just the 2 dimensions in the picture, like X and Y. But now with this one, you also have the 3rd dimension, which would give you the the time going from one picture to the next frame. So it is also encoded, and that gives you a 3D 3D convolutions here, spatio-temporal convolutions. This is the biggest advantage of Akida 2.0. Other advantages would be we can quantize to 8 bits now, as well as and run more and more of the latest models, which are available also on our website in the Model Zoo. So that's Pico. Pico is our smallest implementation. It only takes basically one of the NPUs, and this one is super small. It is 0.2 square millimeters. Only just one. It only has like one NPU on it. Really small, very low power. We're talking about 1 milliwatt here. 1 milliwatt. Good, and this is, yeah, these are the use cases where Akida 2 can actually really shine. First one is, as I said, the later versions of the well-known models like YOLO v5 can be run. It was YOLO v2 only when we had the first version of Akida. Then the TENS, TENS. This state space model helps with with the use cases where you have movement, that as well. And in the end, what I wanted to show you is how an autonomous car can predict its way of going through the city here by taking into consideration how the other cars are actually moving around it. Good, and this is what I wanted to say. Thank you very much.